This diagram shows the gravitational field pattern around the Earth and the Moon. The closer the lines are to each other, the stronger the field. So on the surface of the Earth is where the field is the strongest because that's where the lines are closest together. I'm going to add on some equipotentials now. So equipotentials are lines where the potential is constant. For example, these over here, they have the same potential along each red line, and each red line here, the potential is separated by the same amount of potential difference, which is 5 kilojoules per kilogram. And the closer the lines are to each other, the steeper the potential gradient, so the stronger the field. So again, the closeness of the field line and the potential shows the strength of the field. And you can see on the surface of the Earth, the field lines are the closest together, and the potentials are close together, so the field is strongest. And similar on the Moon, you can see the field lines are getting closer and the potentials are getting closer together. There's a stronger field there. And where the lines are further apart means the field is weaker there. Second thing to know is the relationship between the equipotentials and the field lines. For example, let's focus at this point here on the top. You can see the potential is at 90 degrees to the field lines. Let's look at another point. Again, it should be 90 degrees, the equipotentials and the field lines. Again, this point over here is 90 degrees. So whenever you're drawing an equipotential pattern or a field pattern, you need to make sure that the field lines and the equipotentials are always 90 degrees to each other. The diagram shows equipotentials around a cloud of gas at gravitational field lines. Okay, let's start on the left here. As you can see, the numbers are getting more and more negative as you get closer to the cloud of gas. And this is what we expect, because at infinity, we define potential as zero, and it becomes more negative as you get closer to the mass. So we expect the field pattern to point towards in the direction of the numbers getting more negative. Okay, and on the left-hand side, you can see the equipotentials are close to each other, so we expect the field pattern to be stronger there as well. So I'm going to draw my field pattern like this, ensuring they're at 90 degrees to the equipotentials, and I'm going to point them in the direction of numbers getting more negative, potential getting more negative. On slightly towards the right of that, you can see the lines are starting to space apart more. So that means the field lines are going to be spaced apart as well because the field is getting weaker. And I need to also ensure that this is at 90 degrees to every equipotential is at 90 degrees to the field line that I draw at those points. On this side, it's again the same thing, but it now is pointing towards the right, ensuring it's at 90 degrees. And then it's going to get stronger again as the equipotentials get closer, 90 degrees pointing in the direction of the more negative potential. On the given axis, add a line to show how the gravitational potential varies between the Earth and the Moon. We previously saw that the gravitational potential follows this equation, V equals minus gm over r, so it's negative, and it's an inversely proportional relationship. So it's a reciprocal graph which doesn't touch the axes. Okay, but then the Moon will have a similar pattern as well, but it will be based around the Moon, and it's going to be smaller because the mass of the Moon is less, so it'll look a bit like this. We need to add these two patterns together to get the gravitational potential between those two as a result of those two adding up. So that looks a bit like this. Okay, so you look at the important features of this graph. Firstly, the most important from a potential graph against distance is that the gradient is equal to the gravitational field strength or negative of the gradient. Okay, so let's look at the gradient on the surface of the Earth. That's where it's going to be the steepest gradient because we know the gravitational field strength is the strongest there. And then especially compared to the surface of the Moon, where it's going to be roughly a sixth, so 1.6 newtons per kilogram. So you can see it should be weaker on the surface of the Moon, so less steep. Then the field strength will get weaker, so the tangent here, the gradient should get less and less steep. And there's going to be a point where the gradient is going to equal zero. That's where the gravitational field strength is equal to zero. Okay, because this point is going to be closer to the Moon than it is to the Earth because obviously the Earth's mass is much bigger.